ISA, instruction set architecture. It's a fundamental component in this modern computing era. Its function as an interface in between software and hardware. ISA also defined as a set of instructions that can be processed to be executed. This compatibility enables hardware innovation while maintaining the software functionalities. Computer doesn't understand the mathematical operations like humans do. Instead, they rely on the instructions that specify the operation that need to be done. Here, ISA instruction set architecture commonly use the assembly language, in which assembly language is a low-level programming language that closely interact with processor. Here, we're gonna see the 4 different kind of instructions. Instruction 0, address, 1 address, 2 address, and 3 address. All these addresses require a basic arithmetic operation such as additions, subtractions, multiplications, and divisions. But on the other kind of address like 1 and 0, it requires some extra operations, in which we're gonna explain deep later. First, let's jump to the first operations, 3 address. General purpose register architecture, in which it's only included 2 address and 3 address. For 2 address, it's only required 2 operand like this. And for the 3 address, it requires 2 operand like this. Both of these address only require a basic arithmetic operations, and there is no any additional operands except for 2 address. It's require move. For this address, it will make the flow of the calculations much efficient, and it also helps to reduce the number of instructions. Next, for the second instruction format, we have accumulator registrations. For accumulator registrations, we only use in 1 address, like this. In 1 address, it's only required 1 operand to proceed the flow. In 1 addresses, we have an extra operation such as load and store. Its functions to transfer data from the memory and accumulator. For the third one, we're gonna talk about a stack architecture, in which it's been used in a 0 address. For stacking method, we use LIFO, last in and first out. It also requires an extra operational such as push and pop. So here's our first example. In this example, we're gonna use 3 addresses. But before that, let's recap. For 3 addresses, there will be 4 operations that we're gonna use. First, we have additions, we have substitutions, we have multiplications, and we have divisions. To begin with, first, we have to understand the priority of operations. We have to know who will be executed first. For example, we have brackets here, we have times, and we have plus. In these situations, we need to prioritize the column, the bracket, and then we have to do inside it, in which we have to do multiplications, and then we're gonna do additions. It's happened based on the priority of the mathematical operations. This operation can be stored in a temporary register. For our case, we're gonna use X, Y, and Z as our temporary register. To begin with, here, in this question we have a bracket, so we need to prioritize the bracket. So first, inside the bracket, we have the B plus AC, in which times multiplication is the next under the bracket priority. We're gonna put the multiple mul using the X as a temporary register times A times C. So here it's actually in the operations is equals to like this. So here we already have the A times C. Next, let's continue by adding the B. So add X, we store in the same register B plus the X, in which this X is A times C. So here we can see that the X has already updated and it have the B plus the A times C. So for now, we have done the first part for the bracket. Next, in this first shape, we can see there is A square root 2. A square root 2 equals to A times A. So here you can do, as you already see that the X register has been used. Now let's use the Y because it's near to the first operations, in which it will be much easier for us to execute at the last. So let's do next. We do the multiplications. Y A times and A. In this, it shows that the Y register equals to A times A. Also equivalent to the A square root power of 2. Next, let's complete the upper first. So here, A power of 2 minus B plus A times C. This one and this one we have already done in different register, and we need to do a substitutions in the middle. So to do that, we require to do the sub. Okay, and then we store inside the Y because Y is near into everything. So Y, and then we put the first part A to the power of 2. We put Y and X, in which here the Y register already been updated, in which it shows that Y A to the power of 2, here the first Y to the power of 2 sub with the X. Okay, so here it's gonna be B plus AC. But before we can do the divisions, we need to done the A times D first. So A times D, we can do mul. We store in Z A times D, in which it's equivalent to Z A times D, like this, in which is already the same as this one. So now we need to complete it by divided. So to do this, you have to do the operation of diff, put it as a diff, and store it in the Y, because Y is our main register here as it's been shown. So Y, and then we'll be put this upper in which here in register Y. So we'll put it another Y, AD here as in the register Z. So from these final operations, the output is Y, and then for this Y is A to the power of 2 minus B plus AC over AD for the Z. For our final answer here is the same as what we really want it to be. So here's the flow for the 3 address. Next example, we're going to use a 0 address. 0 address is a little bit complicated to compare with the other kind of address that we have learned before. In this address, it's required 2 extra operations like pop and push. Function of push is to insert the new input like the alphabet or the number. For the pop, its function to show the final answer or to store in the final register. For 0 address, it uses the stacking method in which it uses last in, first out. So here, to complete this, first we need to pop all these 3 before it makes the 2 over D plus 5. So all that we can do is, first we have to add the A, push A, and then we need to push B, and then we need to push C. To make it clear, let's use a graphical explanations of stacking. We push A will be the first level, and then we push B, gonna be on the second level. And we push the C. Here, the operation will happen on the first 2 upper level, in which the first and the second one. So here, as we can see, we have the C, B and A. We can do that the B will times with C. So we're gonna put the mul, in which here it will show the function where the air are not be touched, and then it's gonna be B times C. We're gonna use multiplication operation at this first 2 stacking. So it's gonna be B plus B times C. So here we have done this one, this part. Next, we need to put sub. It's equivalent to the stacking where it's gonna happen A minus B times C. So we already have our first operation here. Next, we need to do this part. So here we can push the 2. We're gonna push 2 we're gonna push D, and we're gonna push 5, in which in graphical explanation it's happened to be where here is our last stacking, so we need to put it A minus B times C. When we push 2, same to this one, we have to push D, we're gonna push 5. So here, all of the numbers and alphabet that we want are already in the stack. Next, we have to do the operations. So first operation is between D5 and D. So here we need to add, and which is going to happen D plus 5 in the same box, 2, and the last one, and one stack is where we're gonna divide the 2 and the D plus 5. So we're gonna put modif, in which is going to happen 2 over D plus 5 and A minus B times C for these operations. Now, as we can see, we already have this one and this one. For our final answer, we have to put the add, and it happened to be in one last stacking box is going to be A minus B times C plus 2 D plus 5. We already have the whole thing in one stack. It's not end yet. Don't forget to pop, in which we have to store in Z. So do the pop Z, and the output lastly will be Z equals to A B times C plus 2 over D plus 5 in one stack. And here is our final answer for these questions. To understand the flow of zero address, we have to know how to tolerance with last in, first out.